products through a big expertise in microbial metallomics, which is quite an exciting topic. So today the talk is about endometriosis and unlocking the microbiome signature in this disease. The floor is yours. Thank you.
Thank you. Yeah, so quick confession, I'm not a doctor, and this is also the very first time I have ever done a presentation like this in my life, so I'm super nervous, but also I'm super excited for this opportunity to share with you today, because I think this is going to be one of those things where you're kind of going to see it and you won't be able to unsee it. So with that, my name is Pendergrass, and I am the founder of Microbiome Signatures, and I'm going to attempt to cover as much as I possibly can in 15 minutes or less. But unfortunately, in order to do that, I'm going to have to read some of these slides word for word. I have no conflicts of interest, so let's get into it. Oh yes, click. All right, so the following are cited as the primary bottlenecks causing the lag between microbiome science and microbiome medicine. So we have lack of high quality RCTs, lack of standardization in methods and analysis, complexity of the microbiome, and mechanistic understanding. No. Yes, okay, so already it's time for a poll. Based on those bottlenecks I just said, when do you think microbiome science will have the potential to reach clinical application? Show of hands, who thinks 30 to 50 years? Well, most people think it's 30 to 50 years. We do have chat, GPT, AI. Okay, all right, good, I'm glad you don't think that anymore. 20 to 30 years. Anyone, 20 to 30? Okay, 10 to 20? 10 to 20, okay, cool, all right. 0 to 5 years. Dope. All right, is there anyone in this room that thinks that we could have already been doing it for the past 10 to 15 years? Nice, nice. What's up, people? All right, so for context, in 2008, I was perfectly healthy, but by the end of 2009, at the age of 25, I'd been diagnosed with the following: PCOS, PMDD, schizophrenia, good times, grade 3 anemia, cirrhosis, a kidney mass, reflux, peripheral neuropathy, optic neuritis, bacterial vaginosis, menopause, misdiagnosis, by the way, ascites and chronic edema, endometriosis, and finally, celiac disease. And not to mention, I gained 50 pounds or 24 kilos in 3 months, literally 3 months. So I basically looked like a giant gray balloon. Fun. Because of all the sudden onset of all of these diseases, I asked myself what I thought was going to be a simple question. What if these are not separate conditions at all, but are symptoms of something else, something bigger? And if so, symptoms of what? Dysbiosis, clearly. So thinking of my diagnoses as symptoms of a larger problem led me to the discovery of the microbiome back in 2010. And that's when I found out that my conditions had overlapping signatures. And after I pieced the signatures together and I got a more coherent pattern, I began figuring out how to decrease the pathogens and support the more beneficial ones. So I read everything I could get my hands on, which, as you can see, at the time it wasn't very much. And despite the fact that there are only dozen or so relevant papers, somehow that was enough. So briefly, I would like to cover my conditions today. This is a lie, because when I got here to Amsterdam, I remembered I have seasonal affective disorder. Okay, so that said, today's presentation isn't about what I did, it's about how I did what I did and what that looked like. So, ladies and gentlemen, this is an accurate representation of what that looks like. And for the record, people like this have to read off their index cards to meet strict time limits. Jokes aside, this kind of all over the placeness is what I think this entire field is missing. Pattern recognition and connections made from interdisciplinary fields mixed with complete and utter desperation. Next, I bet you're thinking this is an unnecessary slide for a room like this, but alas, it is not. So what is a microbiome signature? Well, microbiome signatures are commonly reduced to lists of differentially abundant disease-associated taxa judged by reproducibility and statistical significance. However, it is because of this very definition that many researchers have argued that a definitive microbiome signature is completely unattainable given regional differences and inconsistent methods. Now, my contention is that a true microbiome signature has to be more nuanced than that. First, imposing standardization to resolve variability risks systematic bias, and I personally think that's a terrible idea. Second, a microbiome signature has to ultimately provide a framework that incorporates and tolerates regional differences in microbiota and inconsistent methods. And third, taxon-centric framing like that is rigid, non-intuitive, and makes translational research unnecessarily difficult. So let me ask you here, people of the audience, what is the point of this data if it isn't translational? What is the point if it doesn't give us a first principles understanding of a disease? What is the point if it doesn't help us connect the dots, form hypotheses, or develop novel interventions? And most importantly, what is the point if it can't even support predictive modeling or ultimately save lives? Parsing through the literature while trying not to die inadvertently offered some distinct advantages. So let me show you how I've been doing this for the past 15 years. If you have this PDF, this one's on your chair. If you have it, now is the time to have it in front of you because this next part is going to be a lot. All right, number one, the Metallomics signature of endometriosis. Raise your hand if you've ever heard of a Metallomics signature. Dope, all right. What about microbial metallomics? Anyone in here? Dope, okay, well, that's a couple of you. All right, so the Metallomics signature in endometriosis is characterized by elevated zinc, iron, cadmium, lead, and nickel in the tissues. I don't need that right now. Let me set that down. Number two, environmental exposures. This includes smoking, stainless steel cookware, pesticides, especially organophosphates, water, cosmetics, jewelry, retrograde menstruation, which is technically a microenvironment exposure, and diet, which is the biggest one of all. Number three, nutritional immunity. These are the host defenses to the metallomic environment that are increased. Calprotectin chelates and sequesters zinc. Lactoferrin chelates iron but also nickel. Transferrin chelates iron locally. Hepcidin is increased in the presence of high iron and decreases during iron deficiency, and lipocalin-2 is a siderophore binding protein, and those are all elevated. Now glutathione is decreased, and that's a problem because of all the nutritional immunity factors mentioned. It's the only one that can chelate cadmium and lead. And speaking of cadmium and lead, number four, mismetallation. Cadmium and lead both enter the cell through the calcium channels, displacing correct cofactors like zinc or iron, ultimately leading to hypoxia. However, when cadmium and lead are combined in the environment, they have a synergistic effect and produce even more oxidative stress. Then, number five, taxa with robust toxin antitoxin systems. So taxa with more robust efflux pumps, or those that can survive iron-rich pro-inflammatory environments, will outcompete taxa that don't. Number six, and the taxa that persist often use zinc, iron, and nickel as critical cofactors for metalloenzymes, including zinc-dependent metalloproteases. It's up there. This enzyme uses zinc as a critical cofactor that helps bacteria degrade host tissues and inhibit the host immune system. Nephrate hydrogenases 1, 2, and 3. These are iron and nickel-dependent enzymes that decrease local oxygen saturation and create a hypoxic environment, allowing a suitable environment for strict or facultative anaerobes. Then you have nickel-dependent urease, which increases local pH via ammonia and carbon dioxide, which is definitely a problem for your vaginal lactobacillus that need a tightly regulated pH. And then there's nickel-dependent glyoxylase, which allows for persistence against neutrophils in the blood, Jessica, and this is the specific enzyme that allows these taxa to persist in the blood. But I have to come back to that. Number seven, features. Next, we have beta-glucuronidase, and beta-glucuronidase positivity involves increasing hepatic estrogen recirculation from estrogen G-conjugation, which is a hallmark of endometriosis. Then, siderophore expression. Siderophores are produced by pathogens to chelate and uptake iron from their host or environment, which is essential for their growth and biofilm formation. Then, facultative anaerobes. And the problem with facultative anaerobes is that in order to survive in a low oxygen state, they have to switch to fermentative metabolism. But then, the lesion microenvironment becomes acidic, zinc and iron rich, pro-inflammatory, which in turn is growth promoting, further amplifying latent survival and invasions, which perpetuates the condition. Do you see that? You see that? No, nodded heads. Yes, do you see that? It's cool. All right, moving on to taxogen. E. coli are disproportionately high in endometriosis, and it has all of the zinc, iron, and nickel-dependent enzymes, plus the mechanistic ability for estrogen deconjugation. Notice it ticks all of the above enzymes and features, so it's easy to see the role of E. coli that it plays in this framework. Bacteroides fragilis. It also utilizes zinc as a critical cofactor for its main virulence factor, the B. fragilis toxin, BFT. It expresses a super iron-dependent hydrogenase and even pirates iron from other microbes. And expresses beta-glucuronidase as well. It's a strict anaerobe, so its presence spells trouble and hypoxia. So strep agalactiae, aka groupie strep. Zinc and nickel are critical cofactors and express beta-glucuronidase. It also pirates siderophores. Fusobacterium nucleatum, zinc and nickel are critical cofactors for its enzymes and persistence. It's also interesting because it decreases local oxygen levels primarily by metabolizing and consuming oxygen. However, it is not directly involved in estrogen deconjugation. Candida, this is one of my long cards. Let me explain. I once listened to someone describe Candida albicans as an incidental finding and dismissed it as noise in the context of endometriosis. So let me tell you about Candida in the context of endometriosis. In this signature, Candida biofilms consume oxygen, which results in anaerobic pockets that allow for obligate anaerobes such as B. fragilis and F. nucleatum, and in a hypoxic state, facultative anaerobes switch to fermentative metabolism, like I said. But it also needs to be said that there is solid evidence of tight coadhesion and reduced cytokine output when there are co-aggregates of Candida with F. nucleatum, which suggests functional shielding. Candida also enhances epithelial colonization of group B strep. Not to mention, Candida creates mixed biofilms with E. coli and reduces host defenses. This is also consistent with functional shielding. So, also other studies that found that nickel significantly increases the biomass of the biofilms in these co-aggregates. Nickel. So just to be clear, this is not an incidental finding and this is not noise. This is a problem that 16S studies are not detecting, and researchers, in my opinion, have got to take microbiome signatures finding a step further and look at the relationship between the taxa before dismissing anything as noise. Lactobacillus. Okay, lactobacillus. Lactobacillus is enriched in the gut and peritoneum, but decreased in the vaginal cavity. Translocation is likely the culprit, as the gut microbiome is also a better predictor of endometriosis than the microbiome of the vaginal cavity. It is also nickel dependent and glyoxylase positive. Finally, we have Lactobacillus and Ruminococcus, which are likely decreased simply because they didn't have the right defense systems to survive in the iron-rich environment, and that's it. So moving on to number 9, dietary interventions. So clinically evaluated dietary interventions for endometriosis include a low red meat diet, a low fat diet, a diet with increased citrus fruits, an avoidance of brassicaceae, and a low nickel diet. And this makes total sense. A low red meat diet reduces free iron and zinc. A low fat diet works well if E. coli is the major pathogen. Citrus fruits reduce circulating LPS and were found protective, especially in smokers, while increased brassicaceae consumption was found as a risk factor for endometriosis. And members of that family are cadmium, lead, zinc, and nickel hyperaccumulators, which is already elevated in the Metallomics signature. See, that makes sense. So, question, who in here has ever heard of a low nickel diet? Dope. Okay, there are several studies that have found that a low nickel diet shows promise for endometriosis. Several studies. But even the researchers involved in those studies have said they don't quite understand the mechanisms behind it. So I really want to stress this next point. Glyoxylase positivity enables their persistence because it enables them to evade neutrophils. Without glyoxylase, they become susceptible to immune responses. But keep in mind, glyoxylase is a nickel-dependent enzyme. Remove the nickel and you cripple all of the pathogens. You see that? Beneficial microbes, since that's what we're here for. E. coli Nissl, which is often genetically modified, by the way, is one of my favorite probiotics on the planet. It lacks virulence genes, it outcompetes pathogenic strains of E. coli, B. fragilis, group B strep, Fusobacterium nucleatum, Candida albicans, and other important pathogens, including Klebsiella pneumoniae and Salmonella typhimurium, because not only does it have more sensitive siderophores and thus better iron acquisition systems, it also uptakes nickel and competes even in a hypoxic environment. There's also Saccharomyces boulardii, shout out. Another one of my favorites, which is non-pathogenic fungal species that can outcompete Candida, and its cell walls can also bind cadmium and lead. Love it. Novel interventions. Using this microbiome signature framework, one could easily have predicted that HBOT would be beneficial due to the sheer number of strict and facultative anaerobes in this signature. And guess what? HBOT was the only intervention I had ever come across in 2 years of looking that mentioned complete remission in the animal model. However, it hasn't been clinically investigated in humans yet, and it probably should be. Yay, last slide. Okay, we're gonna do a stop analysis together. So let me recap the following. Increased dietary zinc and iron are associated with an increased risk of endometriosis. The literature consistently shows that lactoferrin and calprotectin, which sequester iron and zinc away from pathogens, are already elevated. The literature also shows that hepcidin is increased in endometriosis, which is an indicator of functional anemia and not true iron deficiency. This signature also shows that key pathogenic taxa express zinc-dependent metalloproteases and advanced iron uptake systems that enable them to degrade host tissues and inhibit the host immune system. Doctors often find that endometriosis patients have anemia or low serum zinc and prescribe iron and zinc supplementation, which clinically, should add, is found to exacerbate symptoms. So let me ask you, question, does the routine recommendation of iron and zinc supplementation make sense based on the microbiome signature that you just saw? Yes, no, 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 no. Congratulations, if you said anything. You just used a non-exhaustive microbiome signature to shape a clinical recommendation, and you did it in 15 minutes if I was successful, of course.